now we will be talking about path independence in a given line integral. So what this concept talks about is that a given line integral will be path independent if for a given domain D, and we are evaluating the line integral from a point A to a point B using different kind of paths. So for instance, we have this form. This is the domain D, this is the point A, and this is the point B, and we have different paths from which we are integrating from A to B. And we can see that no mattering what path we are selecting, either this one or this one or this one, for any case the integral will be equal. It will give the same result. That's what the path independence is telling us, that no mattering what path the integral is following, the result will be always the same. So we know that a line integral is defined as follows. However, we can also write it as this, where we have f1 dx plus f2 dy plus f3 dz. Alright, so this can also be seen as the dot product of two vectors, dx dy dz, where this one is dr, sorry about that, this is f. That's pretty clear from the last video of line integrals. However, whenever we have a line integral that is path independent, we can be assured that we can integrate or evaluate this integral using the next formula. f1 dx plus f2 dy plus f3 dz would be equal to f evaluated at B minus f evaluated at A. But what is f? So here's where we can determine some of the main characteristics that these line integrals would need to have in order to understand it as a path independent line integral. Thus, f what f is telling us is that the vector function f will be equal to the gradient of f. If this condition is success, this occurs, then we will be saying that the line integral is path independent. So we have one condition, that f is equal to the gradient of a scalar function f. So if this is satisfied, then the line integral is path independent, and we can evaluate it as this. So we don't have to make all these calculations. We just need to substitute the value of b in the scalar function f, and the value of a in the scalar function f. Okay, but we also have another condition. So suppose we have this kind of domain, and we have the point A and the point B. So another condition for a line integral to be path independent is that the integral is evaluated in a closed curve. So we're evaluating the integral from A to B in a closed curve. So what that is telling us is that the line integral will be evaluated in a closed curve. And for instance, well, that's just going to give us a 0 as a result, and also we can conclude that that is path independent. Alright, so another condition is that the line integral is evaluated a closed curve. And the third one and last one is that the curl of f is also equal to 0. And what this is telling us is that the derivative of f3 with respect of y is equal to the derivative of f2 with respect of z. The derivative of f1 over dz is equal to the derivative of f3 over x, and that finally the derivative of f2 with respect of x is equal to the derivative of f1 over dy. So if all this is satisfied, then the line integral is also path independent. So that's the last condition, that the curl of f is equal to 0. Given that these three conditions, or any of these three conditions, is satisfied, then we can conclude that the line integral is indeed path independent, and thus we can evaluate it with this formula, making it more easy for us to evaluate this kind of line integrals.